Well, there's a lot of examples, so we may not get through them all today. But if we don't, then I'll put them up online, and you can refer to them if you need an extra to look at an extra example when you're doing the practice. Yeah, Alex. Yeah. Okay, determine if the following is true. So this is the kind of thing that to be able to do the proofs, I mean, we're not doing a proof right now, but like this is the kind of stuff you want to be able to just understand what this is saying. Be able to kind of parse through this sentence on your own and figure out what it's implying. If f at x is p at x times q at x, assuming that p at x and q at x are differentiable again, then f at x, so if f at x is the product of two functions or expressions, then the derivative of f is the product of the derivatives of those functions. That's what this is saying. That was true for the sum. We haven't seen the proof. We'll try to look at that tomorrow for the sum of two functions, but we stated that already, that is true. Is it true for products of functions? How can we figure this out? I wanted to give you some time to try to work through this on your own, but I think we're going to have to kind of just go through it because we're running out of time. So I'm going to get you started. We'll just pick some. So I'm going to do 6x to the 5. I just picked like random, whatever. So in that case, what's the derivative of that function? John? Very good. See, nothing crazy yet. Can somebody help me break that function up into the product of two other simple functions? This is where you need a little bit of creativity. This is definitely something you're capable of doing, if you just understand what it's asking. Yeah. Thank you. Right? Do you agree that that's equal to 6x to the 5? And now f at x is the product of two other functions. So this would be p, and this would be q. So p prime 2 times 3 is 6, and reduce the exponent by 1, so 6x. And q prime 3 times 2 is 6, and reduce the exponent of 3 by 1 is 2. Should you agree with that that's the derivative of each of those individually? Yes? No? Are we okay with that? 6x. So if this is true, is anybody looking ahead? Do you see what's happening here? And then if I simplify, what do I get? 36 x cubed. Not equal. Therefore, f prime is not equal to p prime times q prime. Not, right? This is like one of those things. Don't make this mistake. I don't think you will, because it's kind of a big deal what we learn, and we talk about it a lot, and we do it a lot, and over the course of the next week and a half, you're going to learn a few more rules similar to what we're going to do today. So I don't think you'll make this mistake, but you never know. Sometimes we're thinking about something else, and we revert back to our intuition. We forget that it's a lot more complicated than just this. When you sum, yes, you take the derivative of each individual part and just sum the derivatives. When you have a product, this times this, no. We just proved. To prove something's true, you need a whole formal proof. Prove it for every case, the general case, using k's for constants and all kinds of fancy stuff. To prove something's not true, one counterexample is enough, right? So there you go. Not true. So what is true? There it is again. And P and Q are differentiable, then F prime equals, put your pencil down and watch. And you're gonna, this is the kind of thing where you're probably gonna, like, as you're doing your practice, you're gonna say this over and over and over again in your head to the point where you memorize it. The derivative of the first times the second plus the first times the derivative of the second. Let's use our other example, which was 6x to the 5. We did, I think, 3x squared times 2x cubed, right? Is that what we did? So how would I use this formula? The derivative of the first, so the derivative of 3x squared, which is 6x, times the second, which is 2x cubed, plus the first 3x squared times the derivative of the second, which is 6x squared. 6 times 2 is 12. X times x cubed is x to the 4th, plus 3 times 6 is 18. X squared times x squared is x to the 4th. Adding the exponents, 12x to the 4th plus 18x to the 4th, 30x to the 4th. That's not a proof. Showing it's true for one example doesn't prove anything, but at least it worked. Right? So this was like derivative of the first, right? And then all of this, and basically the rest of this unit, is all about like building skills and practicing our skills to be able to take derivatives of bigger, more complicated expressions. That's what this is all about. Questions, questions, questions. All right, let's try something. So this is my P, this is my Q. And normally I wouldn't do this thing off to the side. But P prime, if I take the derivative of P, I'm going to get, so 5x squared, that's 10x plus 3. And Q prime is 6x squared minus 16x. Yeah? Usually we just do that differentiating in place. What's the formula? Derivative of the first times the second plus the first times the derivative of the second. Derivative of the first, so P prime, which is 10x plus 3, times the second, 2x cubed minus 8x squared minus 5, plus the first, 5x squared plus 3x minus 7, times the derivative of the second. Derivative of the second. I mean, it's not that bad because you're going to take the derivative of each part and then just multiply it by the entire other part. So one time you're taking one derivative, and not the derivative of the other, and then the other time you're flipping it, right? So once you do it a few times, you kind of, it's not too hard to memorize. And in this case, you got to know that then you add those parts. Don't multiply the parts or do anything else. You're adding the parts, right? And that one would be a disaster to expand. We're not going to right now. Whether or not you have to expand just totally depends on what you're doing, what the instructions are, that kind of thing. I don't imagine that I'll be all that interested in, making you expand something like that. You might have to once on a quiz or a test or something, but not a ton of times. That's not really what we're interested in. So sometimes you might be able to leave it like that. But for some problems, you might have to simplify because you might be solving it and you'd have to fully simplify and then factor to solve. So, I mean, absolutely, it's the kind of thing you might have to do down the road, but we're not going to bother today. All right, I want you to give this one a try on your own. And you can simplify this one. So if this is my P and this is my Q, I take the derivative of the first part. What's the derivative of the first part? Mary Lou, what'd you get? That's the derivative of the first part? 3. Very nice. Times the whole second part. Plus the derivative of the second part, which is 4 times the first part. Expand. 3 times 4x is 12x. 3 times negative 5 is negative 15. Plus 4 times 3 is 12x. 4 times 7 is 28. And what happens when I simplify 12x and 12x is 24x. 28 minus 15 is 13. And just notice, I'm sure you already have, that what I did separately was I expanded these binomials to get the kind of thing that we could already differentiate a couple of days ago and just show you that, hey, it worked out. So either of those two ways is fine. If you had done it either of those ways in this case, unless the instructions of the question said use the product rule or something like that, but otherwise, you could kind of do it however you want. Good? Just going to keep doing more examples. What's another way I could think of this? Yella? So y prime, derivative of the first times the second, plus the derivative of the second times the first. However you choose to expand and simplify this, I'm actually going to collect like terms here, which is a strange thing to do, but the brackets are the same. I've got 3 of the bracket and 3 more of the bracket, so I've got 6 of the bracket. If you don't like that, you could expand the brackets first. Done. Good? That was a simple one. That was the reason why we did that. because we could have done it another way. So the power of a function, so we had a function and we raised it, like a whole function, an expression, and raised it to an exponent. Well, we do have a rule to take the derivative of that directly. And so if you had a more complex function, which we will certainly see down the road in this course, or if it was even just had 3 or 4 terms and you didn't want to do the whole expansion thing, then you could do it this way. So if f at x equals g at x all to the n, and g at x is differentiable, then f prime is n times g at x to the n minus 1. Where do you recognize that from? Mason? Yeah, that's the same thing we've been doing. 3x squared, derivative of 6x. Pull the exponent out in front, multiply, and decrease the exponent by 1. But it's not done yet, times the derivative of what's inside the brackets. I hope we would assume you can't just ignore what's in the brackets, right? It's going to have some role to play. So times the derivative of what's inside. So let's try this question again. I take the 2 down in front. Subtract 1 from the exponents. 2 minus 1 is 1. Times the derivative of what's inside. What's the derivative that's from inside the brackets? 3. 2 times 3 is 6. And look, we got the same thing. In a case like this, I don't know that that's easier. But if it was a fractional exponent or a negative exponent or some other kind of exponent, then you might not be able to do it the other way. So you'd have to do it this way. So this is certainly something that you need to be able to do. Why don't you try D? So we multiply the 4 out front and then subtract these 1. That should feel very familiar. Times the derivative of what's inside. What's the derivative of what's inside? 3. And then if I simplify, bring that 3, I get 12, 3x minus 7 all cubed. We're not going to bother expanding that. If you had to, then it would be really useful if you were brushed up a little bit on the binomial theorem and how to expand that in one step, one line, without having to actually do it in multiple steps or anything like that. Any questions? What do you think we're going to do for this one? Very good. We're catching on, I hope. And really starting to see square roots as exponents. And we know how to work with exponents. So we pretty much always change roots, square roots, cube roots, whatever it is, into an exponent, right? make sure that you put this, and you don't just say equals, equals, equals. Some people were doing that, I think was on a test or a learning goal or a quiz or something recently, and like it wasn't equal to, because it's the derivative now. So you got to kind of state where you're starting to do the derivative, right? This next line's not equal to the line above it, because it's the derivative of that. So you have to put that. So 1/2 3x squared minus 2x plus 7. 1/2 minus 1 is negative 1/2. Times the derivative of what's inside. What's the derivative of what's inside? So 6x minus 2, it looks like to me. Now this is one where we certainly would not leave it like this. So a negative exponent does what? Reciprocal, right? So it's going to move that part into the denominator. So if I just sort of analyze this, this is going to be in the numerator. This is going to be in the denominator. That's in a denominator. This is all multiplied together. So I'm going to get 6x minus 2 over 2 times 3x squared minus 2x plus 7 to the 1/2. And I could turn that back into a square root. You wouldn't have to. But just to remind us that that's what's happening, I'm going to. Oh! What else can we do? Almost missed it. Yeah, we can factor, right? So I end up with 2 times 3x minus 1 over 2 square root. That's just a fluke, I think. Questions, questions, questions. We've got a few more examples to do. I don't want to run out of time. We're going to have to skip at least one. Got 3 more here. 1, 2, yeah, only 3, but we only have 7 minutes. So here's an example where we kind of need the power of a product rule that we just saw, and the product, like you're not expanding that, right? So if I think of this as P and this is Q, then P prime is going to be 4 times 5x plus 7 cubed times the derivative of what's inside, which is 5. So that works out to 20, 5x plus 7 cubed. And Q prime is 5 times 2x minus 9 to the 4 times the derivative of what's inside, which is 2. The more complex they get, whoop, I'm missing something there, yeah. The more complex they get, the harder it is to just see it. So if you were doing this, so for a lesson at least, that's why it's nice to kind of write off to the side so that those don't just appear magically. Derivative of the first, 20, 5x plus 7 cubed times the second, 2x minus 9 to the 5th, plus the first, 5x plus 7 to the 4th, times the derivative of the second, 10 times 2x minus 9 to the 4th. Put your pencil down and watch. This one might be a little bit tricky. This is quite factorable. This is why your factoring skills need to be so top-notch. I've got 2 parts. Here's one part. Here's the other part. I'm just common factoring. So the 10 and the 20, I can factor out a 10. The 5x plus 7 bracket, I've got 3 at least in each. So 5x plus 7 all to the 3. And the 2x minus 9, I've got 4 in each. So 2x minus 9 to the 4. And then what am I left with? 2 times 1 of the second bracket, 2x minus 9, plus the 10 was factored out, so 1 times 1 of that first bracket, 5x plus 7. So that's 4x minus 18 plus 5x plus 7. We are going to spend 9x minus 11. We're going to spend a lot of days just practicing how to fully simplify these things and start doing some sort of more interesting things with them eventually. So don't get caught up on, well, when am I supposed to? Because some of those examples we did, some we didn't. Like I said, eventually it's going to depend on what you're doing with it. But we're going to spend a bunch of days on practicing fully simplifying, and it'll be more clearer by the end of that, I think. I got to show you one more little thing, even if we don't do the example. So we're going to skip this example. This one just works with sort of fractional exponents and that kind of thing a little bit more, right? So I'll put it up online in case you want to refer to it. The extended product rule. If F equals P times Q times R, and P and Q and R are differentiable, then F prime, ready for it, equals the derivative of the first times the second and the third plus the first times the derivative of the second times the third. I'm just doing this in order. You could write it kind of however you want. Plus P times Q times R prime. So when you see this one and you make sense of it, then you go back and you kind of see the pattern in the regular product rule. Even easier, I think. Okay, so I'm taking the product of each on its own and multiplying it by every other part. You could extend this to 3 functions or 4 functions or 5 functions, right? P, Q, R, S, T, like it would be the same, follow the same pattern. So we have an example there. Maybe I'll put that one up online as well, but I would have to take the derivative of the first part and multiply it by those. Then take the derivative of the second and multiply it by those. And the derivative of the second, I'd have to use the power of a function rule. And then the derivative of that part, which again, it's a radical, so I'd have to take that into account. So there'll be a lot of work to it, but again, you'd just be kind of carefully going through each part. Any questions? Did you practice?